we go. 5.3b is where we're at. And we're going to write in our first properties of logs that we're going to talk about. These log properties are called our identity and inverse properties. Okay. So first one, log A1. Log A1, that is our identity property. And it's going to equal 0 no matter what it is. Okay. The reason being is any number to the power of 0 is 1. Remember, a log is asking you is what this base to what number makes this argument. Okay. So for example, if we had log of 10, what is the answer? 0. Because 10 to the 0 power is 1. That is 1. Okay. All right. Continuing. Next, log base A of A. This is our inverse property. Okay. If the base of the log and the argument are the same value, they cancel each other out. Okay. If the base of the log and the argument are the same, they cancel each other out and you're left with a 1. Okay. So let's give this a shot. If I had log 5, oh my gosh. 1. Do we see how that works?
Yes.
Yes. Okay. Why? Because 5 to the 1 power is 5. That's how you verify. Okay. Uh-oh, made a little extra mark there. Next, our next property. So this also applies when you have anything other, when you have a power. So when you have a power on your argument, that's going to be all that's left standing. And why is that? That's because your log base A of A is already 1, right? And then all that's left remaining is your X. So this would equal X. So for example, if we had log 10, 4. So log 10, 4. Even though there's no base there, what is the base of that log? 10, because that's our common log. So guess what? This goes away, and all I'm left with is 4.
Oh, okay.
Yeah. I didn't cross the 4. It's still there.
They said 10, and I was like, why is 10 left?
Because
I
that's
thought it
the
was
base
4
of the
left.
log. That was the base of the log.
Oh, I thought you said what's left. Okay, that makes more sense.
Okay. All right. Next one of our inverse properties is if you have an exponential. If you have an exponential raised to the base log with the same base of the exponential, guess what they do to each other?
Wow.
They cancel each other out, and you're left with whatever's there. So if I have 2 log base 2 of 600, what does that equal?
2.
600, because the log of
yeah.
the base of the log and the base of the exponential are the same. Okay. Last rule that we have here. The last rule is that if you have 2 logs that are equal to each other and they have the same base, to solve them, you're going to set the arguments equal to each other. So for example, if we had log 6 x plus 1 equals log 6 of 4, notice that the bases of the log are the same. So all you're doing is taking your arguments and setting them equal to each other. So x plus 1 equals 4. So what is x? 3. Okay, it's the same thing that you learned about exponents. If your bases of your exponents are the same, all you're doing is taking your powers and setting them equal to each other. All right, using one of the above 5 properties, please take a moment and try to solve the equation log base 7x equals 1. What is x? Using one of the above properties. What is x? Looking at my properties, which one produces 1? Okay, using property 2. So in property 2, in order to get 1, what has to be what has to be my base in my argument?
7.
7, because they have to be the same. Okay, and this because we use what property up there? 2. Okay? Yes? All right, how do we feel about inverse and identity properties?
So even if it's like log 7 y equals 1, would it be y equals 7?
Exactly, because the only way to get 1 is that the argument and the base have to be the same. Okay? Got it?
Sir, yes, sir. Ma'am, yes, ma'am.
Okay. All right, let's talk about the log function itself. We're gonna do a little bit of drawing here.
Oh, boy. Oh, boy.
So fake. All right. It says for the function. So we're gonna draw out our log function. So we're gonna. All right, we said that the log function is the inverse of the exponential, right? So thinking about some of the properties of the exponential, what is a big property of the exponential function? Huh? What is a big property of the graph? You just did it, you know, it was the 5.3a. But you said you were gonna do those notes. So then no.
I don't understand them though.
Then show up.
She on the, she basically just said.
It curves.
She basically just said.
Okay. Key thing, it has a horizontal asymptote. So if exponential has a horizontal asymptote, what does log have? If they're inverses of each other, a vertical asymptote. So we're gonna draw in a vertical asymptote at x equals 0. Okay. The other key feature of the exponential is that it has a y-intercept at 0, 1, right? If I'm taking the inverse of something, what ends up happening to my x and my y? They switch, so it becomes 1, 0. So the other key aspect of my log function is that it has an x-intercept at 1, 0. Okay, so my function looks something like this. Okay, so now that we have the function, let's describe what we see. Okay, so for a log function with a greater than 1, is it increasing or decreasing? Is it increasing or decreasing? It's increasing because we read a graph from left to right. That is nice, well, increasing. There you go. Yes. Okay, next it says, what is the domain of this graph? What is our domain?
X is anything greater than or equal to greater than 0.
There we go. Anything greater than 0 for x's, right? So our x is greater than 0, or we can write it from 0 to infinity. What about our range? What is the range of this graph? All real numbers. Our range is all real numbers. It's forever going down and forever going up. And where did we say our intercept was? 1, 0. So analyzing our graph, also the graph has a blank as a vertical asymptote. It has x equals 0 as a vertical asymptote, right? That's my imaginary boundary line. Is that what you're checking on the phone for us, sir?
Sorry, I needed to see something.
Uh-huh.
So
I wonder if I'm on my phone playing soccer, how does that work? Oh, okay.
He's looking for the
Just-
logarithm of the.
All right, here we go. The graph f of x equals log base ax is a reflection of the graph of f of x equals a to the x. So we're gonna draw in our exponential. So we're gonna draw in the exponential. It has the asymptote at y equals 0. It has the intercept at 0, 1. And so it increases from left to right. Now with your teacher trying her very best to draw them somewhat symmetrical. Do you see the symmetry?
Not at all.
I said I tried my best.
It could be better.
You know, guys,
I see it.
Okay, it's symmetrical. It's symmetrical over the line I created, which is supposed to be the y equals x line. Okay, it is the best I can do freehand. Okay. All right. How do we feel about analyzing the log function? I feel like false.
Let's say being confusing.
Yeah. All right, so sketching the graph. So when we are sketching the graph, what we're just analyzing is how it changes. So as you can see, there was supposed to be another graph here. It just, oh, whoa, Pam. Oh,
That's not.
my Pam got angry. It got angry. Okay. I don't either. I feel all the energy in this room and it throws me. All right. Okay, so on the first graph, we're going to graph our common log, which is just log base x. On the second graph, we're going to graph log base 3 of x. You're going to use your calculator to model and to analyze the difference of the two. Okay, so with your handy dandy calculator, calculadora, normally, yes, I try to be better.
Oh, it's already graphed for me. How great.
Because people don't clear their calculators before handing them off. All right. So log, common log means I can just press the log button and type in log x, right? Agreed? Whoa, mine's doing some weird things.
Turn it on.
I did turn it on.
You put,
I don't know why that's funny to you that I have to turn my calculator. It's a calculator.
But on a computer.
It has to be turned on
Why?
because it's a real live version of it. Okay, so now my calculator, continuing at log x, we're gonna graph log base 3 of x. How can we get log base 3 of x in the calculator?
Alpha, window. No.
It's alpha window 5.
There we go. So yesterday we talked about to get the change of base, we're gonna press alpha, window, and 5 allows us to put in that change of base without having to use the change of base rule. Okay, so we have 3x. Or I thought I had x. All right. Yes. All right, so now when we graph, our blue will be our common log and our red will be our base 3. Yes? All right, so we're gonna graph. So there's our common log and there's our log base 3. What do you notice when the base got smaller?
It got smaller.
It got bigger.
It stretched more, right?
Yeah.
It got bigger. My log base 3 got further away from the x-axis. Anyone wants to take a guess as to why that's happening?
A larger exponent.
Exactly. Because our base is smaller, that means that our exponent has to be larger for us to get to the next number or our next value. Okay. So I'm going to do a little sketch of them. Ooh, calculator. So very close. The other thing to note is they both are still going to cross.
Why did you take it all the way from the bottom? If that's not how it is?
Because even though you can't see it, it actually is getting as close as it can to x. The y-axis.
Just trying to see. I ain't trying to be smart. I was just trying to see.
No, good question.
You know how you do.
I get excited. Yeah.
About math.
All right. So again, because your remember logs and exponents are related. When I have the log of something, I'm saying 10 to what power is this? Or 3 to what power is this? Okay, that argument is what I'm trying to define. All right. Okay, that concludes